Hi everyone, a very good afternoon to all of you. I am from I3C team of 2-Chip Solutions and welcome you all to this webinar. Today we are going to present a webinar on I3C. Our agenda of this webinar is to provide the overview of I3C along with the features. Then I will explain the different address assignment procedure and brief about the different messaging modes like SDR, HDR and its submodes. After that, we will go through the 2-Chip I3C VIP architecture and the features. Basically, I3C is an evolutionary standard that improves upon the feature of I2C while maintaining backward compatibility. It will be better suited for handling an abundance of sensors. I3C uses the same two-wire interface as an I2C, where one wire is SDA, used as a serial data pen, and it is bidirectional. And the other wire is SCL, used as a serial clock pin. But for HDR modes, it used as a bidirectional data pen. I3C is designed to overcome some I2C limitations that are in-band interrupts, dynamic address assignment, handling multiple masters, standardizing commands with common command codes, issues with hot joining, error detection, and error recovery. I3C supports several communication formats that are direct and broadcast messaging based on common command codes. It also supports low power, high speed serial interface and other features that are currently covered by I2C. As I said, I3C is a two-viral serial communication protocol, works up to 12.5 MHz using push-pull. There are different messaging modes in I3C like SDR. It is significantly similar to I2C protocol in terms of procedure and conditions. HDR, high data rate messaging modes having multi-submodes like HDR DDR used for double data rate, HDR-TSL used with ternary coding, which includes both I3C and legacy I2C devices. HDR-TSV used with ternary coding and no I2C devices present on the I3C bus. HDR bulk transport. I3C is a standard used for connecting multiple master and multiple slaves at a time. I3C supports multiple address assignment procedures. It supports dynamic address assignment while supporting static addressing for legacy I2C devices. Also support for group address assignment. We go in detail in later slides. Some other features of I3C are secondary master capabilities, slave reset without additional wire, multi-lane data transfer, and so on. The I3C master device is the current or the main master at a time. Only the main master on the bus sends the I3C command, addressing either all slaves using broadcast common command codes or specific a slave using directed common command codes. And it is also allowed to send I2C messages on an I3C bus. Here is the block diagram of I3C. As you can see in this diagram, the color blue indicates the devices with a master role. The color pink indicates the devices with an I3C slave role, and the color purple indicates the devices with an I2C slave role. Also, I3C secondary master devices are shaded from blue to pink, showing their ability to function in both masters and slave roles at different times. An I3C bus can support up to 11 I3C slave devices. For addressing, an I3C slave devices support at least one of the dynamic address assignment procedure methods based on set DASA, set AASA, or enter DA common command code. We can also assign our address to multiple slaves devices on an I3C bus using group address assignment procedure. In I3C, bus slave is also responsible for requesting in-band interrupts, generate hot join events, and also it will request to work as a current or main master only if it has the I3C master device capability and support any combination of I2Cs and I3Cs defined HDR modes. Every I3C device on the bus must be configured using the characteristic registers that define the capabilities and function of an I3C devices. The configuration of an I3C bus will depend upon the characteristic of the I3C devices intended to be active on the I3C bus. Devices without I3C characteristic register shall not be connected to a common I3C bus. Three types of registers are BCR, bus characteristic register, DCR, device characteristics register, LVR, legacy characteristic register. BCR describes the I3C device role and capabilities for use in the dynamic address assignment and common command. As you see in this table displays all the I3C devices role and capabilities. It provides information about type of devices, master or slave, device capability that defines the messaging mode using the getcaps CCC. It also defines whether a virtual slave is supported or not. Device will always respond to I3C bus command or not, and roles related to in-band interrupt. DCR describes the I3C device type. Each I3C device that is connected to the I3C bus shall have an associative read-only device characteristic register. DCR provides 255 available code for describing the types of sensor or device. For example, accelerometer, gyroscope, composite devices. The default value of DCR will be ATIC base 0. LVR describes the device significant features. On the I3C bus, if any legacy I2C device are present, then LVR determine allowed mode and maximum SCL clock frequency. Each legacy I2C devices that can be connected to the I3C bus shall have an associated read-only legacy virtual register. LVR content for all I2C devices is always known by the main master. For addressing, an I3C slave device support at least one of the dynamic address assignment method based on set DASA, set AASA, or enter DAA common command code. We can also assign a address to multiple I3C slave devices on an I3C bus using group address assignment procedure. As I told previously, for addressing an I3C slave device must support dynamic address assignment method. The I3C main master assigns each device a unique address either when the bus is initialized or when a new device is connected to a configured I3C bus. Once a device receives a dynamic address, the dynamic address shall be used in all device subsequent transaction on the I3C bus until and unless the master changes the device's dynamic address. Master can reset the dynamic address either for all devices at once using broadcast version of reset DA or individually with a reference to a specific dynamic address. There are three ways for assigning the dynamic address. First, enter DAA. The enter DAA broadcast command forces all I3C slave devices, if they do not already have a dynamic address assigned, to go into address assignment mode. As you see in the figure, after enter DA CCC, the master sends a repeated start and broadcast address 7TIC-H7E with a read-write bit raised. Each I3C device that does not yet had a dynamic address must acknowledge acceptance with an ACK and send its 48-bit provisional ID with their characteristic register, that is BCR and DCR, concatenated in a loop. In this case, the dynamic address assignment arbitration process is activated, in which the devices with the lowest value wins the arbitration and the master sends the address to it. After that, the device that received the dynamic address stops transmitting its identifier and exits the process. The next device wins the transmission, arbitration, and so on. The procedure always ends with stop. Moving forward to another methods, the second is set DASA. This CCC allows the master to assign a dynamic address to one slave using the slave static address. This is the faster than the enter DA dynamic address assignment procedure. The set DASA CCC should always be used before the enter DA CCC is used. Shown in the figure, the newly assigned address is transmitted in the dynamic address byte, where the 7 most significant bit 7 down to 1, contain the 7-bit dynamic address, and the least significant bit 0, is filled with the value 1TIC-B0. The third method is set AASA. This CCC allows the master to request that all the connected slave use their known static address as their dynamic address. This is the fastest method to assign I3C dynamic address to all the slaves with static addresses. As an optional feature, multiple I3C slave devices can share a single group address, allowing a master device to send a given I3C message to all the slave devices in the group at once, rather than one at a time. To use the group address feature, the current master must support the assignment of group address. The current master shall not attempt to read data from I3C devices using a group address. Group address assignment is performed using set group A CCC. The group address to be assigned is transmitted in the group address byte shown in the figure, where the 7 most significant bits 7 down to 1, contain the 7-bit group address, and the least significant bit 0, is filled with the value 1 tick B0. The same address can be assigned to another slave by repeating the process. The current master also have a capability to reset the assigned group address or remove a particular slave from a group. As I said earlier, I3C have different type of messaging modes. SDR, single data rate, which supports private messaging using direct and broadcast messages. SDR DDR, used same signaling as SDR mode and run at about 2x the speed of SDR. HDR TSL mode, used for higher data rate using ternary coding for buses with a mix of I2C and I3C devices. HDR TSP mode, used for higher data rates using ternary coding for buses with only I3C devices. HDR BT mode gives the highest possible throughput using a clock and data transmission model leveraging dual data rate over single, dual, or quad lane configuration. Now we will go through these message modes in detail. HDR mode is a default mode of the I3C bus and is primarily used for private messaging from the current master device to the slave device. SDR mode is also used to enter other modes, submodes, and states, and for built-in features such as common command codes, in-band interrupts, and transition from I2C to I3C by assignment of a dynamic address. I3C SDR mode is significantly similar to I2C protocol in terms of procedure and conditions. In I3C SDR mode, SDA is used for data transmission and SCLS clock. The figure shows the frame of a SDR. It starts with a start or a repeated start followed by I3C reserved byte, that is 7TIC-H7E, or I3C dynamic address. Then read-write bit for indication of read or write operation, followed by ACK. Then based on direction, actual data byte is transmitted followed by transition bit. A transition bit will be a parity in case of write operation, and in case of read operation, it tells whether the operation is continued or not. The write or the read operation will be terminated with a stop generated by the master. HDR stands for high data rate modes, which allow transferring mode while preserving SDR frequency. HDR does not have any faster clock, but still more bits should be transferred for same frequency. HDR supported devices can be present on I3C bus along with the I2C devices. There are 4 types of HDR modes. DDR that supports transfer up to 20 Mbps, TSL, TSP that supports transfer up to 30 Mbps, and bulk transport which provide 8x, 4x, and 2x and raw HDR rate. For exiting and restarting, HDR mode will use HDR restart and HDR exit pattern. As you can see, this is the HDR exit pattern, which starts with SDA high, SCL low. It detected when SDA falls from high to low 4 times continuously, while SCL remains low for the whole time. After detecting the exit pattern, master generates the stop. For restart pattern, it starts same as the HDR exit pattern, that is SDA high, SCL low. But it detects SDA toggling 4 times, fall, rise continuously. After that, the pausage of SCL validates the restart condition, starts the new transfer. Like SDR mode, HDR DDR mode uses SCL as a clock. However, data and commands changes SDA on both SCL edges, effectively doubling the data rate. The I3C bus enters HDR DDR by transmission of enter HDR0 common command code and exit it when HDR exit pattern is observed. 4 HDR DDR words type are defined: command word, user data word, CRC word, and reserved word. HDR DDR moves data by words. A words generally contain 16 payload bits as 2 bytes in a byte stream and 2 parity bits. The HDR DDR protocol precedes each 18-bit word with a 2-bit preamble for a total of 20 bits per word. The preamble indicates the type of data that follows: command, data, or CRC. If preamble bit is 2TIC B01, then it can be command word or a CRC word. If a preamble bit is a 2-tick B10 or 2-tick B11, then it is a data word. As the figure shows the frame of different type of words used in the HDR-DDR. First one is HDR-DDR command word, started with preamble 2-tick B01. The length of the command word shall be 18 bits, which include 8 bit of command word, 7 bit for slave address, and next bit is reserved and equal to 0, and last 2 bits for parity. Similarly, HDR-DDR data word starts with preamble equals to 2-tick B10 or 2-tick B11. The length of the normal data word shall be 18 bits, where 16 bits at 2 data bytes followed by 2 parity bits. Last is HDR-DDR CRC word. The preamble before a CRC word shall have the value 2-tick B01. The length of the CRC word shall be 10 clocked bits, 4-bit 4-tick SC token, 5 bits of CRC5 value, 1 bit of 1-tick B1 setup to prepare the bus for the following HDR exit pattern or HDR restart pattern. The value of the upper nibble, first 4 bits after the preamble of a CRC word shall be 4-tick HC. There is no parity checking for a CRC word. Here we can see the frame structure of DDR mode. An HDR-DDR mode starts with I3C start followed by master broadcast and enter HDR mode CCC. Then the I3C bus switches to the requested HDR-DDR mode. After that, the master issues an HDR command word followed by 0 or more HDR data words and CRC word, and an HDR restart pattern or an exit pattern. If an HDR restart pattern detected, then a new HDR command is sent. At last, an I3C stop is generated, which ends with the bus free condition. HDR-DDR supports special type of framing for transmitting common command codes. All CCCs that are supported in HDR-DDR modes shall be sent by current or main master. By the figure, HDR-DDR frame starts with a header block, which includes indicator word and CCC command word, followed by a data word, CRC word, and ended when the observed any HDR-DDR CCC end processor. We see the end processor in the detail in later slides. HDR modes, HDR-TSP and HDR-TSL use ternary signaling as on the 2 wires. Ternary signaling effectively communicates 1.5 data bits per time event, which is 50% more than non-ternary I3C signaling. This higher effective data rate is achieved by using both lines, SCL and SDA, for data. The name ternary comes from the fact that each line state change exactly 3 transitions are possible. The 3 possible line transitions are only the SCL line changes, only the SDA line changes, both SCL and SDA changes. The I3C bus enters HDR-TSP and HDR-TSL by transmission of enter HDR1, enter HDR2 CCC, and both exit when HDR exit pattern is observed. In ternary modes, data is transferred in message that consist of command words and data words, where command words is always issued by master and data words may be issued by master or slave, depends on the operation type. HDR ternary mode starts with I3C start followed by master broadcast and enter HDR ternary mode CCC. Then the I3C bus switches to the requested HDR ternary mode. These HDR ternary modes are entered in a standard way, followed by a command and 0 or more data words. After that, HDR restart pattern will be generated if master want to send a new message. And finally, HDR mode is ended by the HDR exit pattern, followed by I3C stop. HDR ternary supports special type of framing for transmitting common command codes. All CCCs that are supported in HDR ternary modes shall be sent by current or main master. The figure shows the frame structure of CCC transmission in HDR ternary. As mentioned in DDR, it also includes a header block, data block, and lastly the end processor. Header block consists of indicator word and CCC command word followed by CCC data word, which contain one or more data words. HDR-BT is provided to give the highest possible throughput using a clock and data transmission model. Based on the number of SDA lanes, 4 for quad lane configuration, 2 for dual lane, and 1 for single lane. HDR bulk transfer provides 8x, 4x, and 2x and the raw SDR rate, respectively, at the same clock frequency. HDR-BT is the primarily aimed at multi-lane buses. It can also be used in a single lane context, providing about 1.2x the real data rate for HDR-DDR. The figure shows the frame of HDR bulk transfer. The frame of bulk transfer starts with start followed by enter HDR or with HDR restart, followed by HDR-BT header block, which is defined as two type indicator words and selector word. HDR-BT header block that begins the framing for a broadcast CCC or a direct CCC shall be referred to as a HDR-BT indicator block. HDR-BT header block that begins a read segment or a write segment in direct CCC framing shall be referred to as the HDR-BT selector block. Then the HDR-BT CCC block, data block, and the CRC block, which serves as the termination marker, follow an HDR-BT CCC header block. At last will be the end procedure, which we will discuss in the next slide. End procedure is used to end the broadcast or direct CCC in all the HDR modes. As shown in the figure, there are three possible ways for ending the procedures, that are end of the broadcast or direct CCC followed by the new broadcast or direct CCC. Second, return to standard HDR transaction or a subsequent exit from HDR mode. Third one, or an immediate exit from HDR mode. Now, this is a true chip I3C VIP block diagram. Here, as you can see in the figure, the multiple master includes main master and secondary master, and the slaves includes both I3C and I2C are connected by the interface. I3C monitor, I3C scoreboard, and the I3C assertions is also connected by the interface. Multiple test suites are also present to test all the scenarios. Now we go through the TrueChip I3C VIP features. The VIP supports all modes of operation. The TrueChip VIP provides a wide range of programmable protocol check along with the bus assertion for all protocol scenarios. Callback functionality is supported in all the components like master, slave, monitor, and scoreboard. VIP provides bus and configuration coverage and also the assertion coverage and achieve 100% in all simulators. VIP support the use of randomization and constraint to generate corner scenarios. Support for dynamic configuration is available. Components can be reconfigured on the fly for each new packet. Provide summary of all the transactions received on bus along with the real-time bus transaction details in log file. Message management, error or warning reporting can be controlled by changing their severity level or by suppressing it. Every error or warning having a unique error ID will provide a detailed description of error, which will be helpful in debugging. VIP provide support for UVM register model and generate rel sequences. It also supports configurable memory map. VIP can support existent I2C bus devices like I2C messaging, single data rate messaging, SDR, etc. It supports all transfer modes, single data rate mode, high data rate mode, that is DDR, TSP, TSL, BT, multi-lane data transfer for both SDR and HDR speed modes. VIP also supports main master, secondary master, and slave devices. It supports pre-handoff flow, master to master handoff procedure, bus management, and configuration procedure. VIP supports both dynamic and group address assignment procedures. VIP also supports the additional multi-drop, in-band interrupt, hot join, and passive hot join capabilities. It supports device-to-device tunneling and device early termination capability for both write and read transfer. The VIP support for TrueY GUI for easy debugging like real-time transaction, latencies, statistics, and many more in tabular and graphical format. Now we will learn about the TrueY in more details. TrueY come with the TrueChip come with the TrueY, the debug tool. TrueY helps in easy integration that will reduce man efforts and time, helps in easy and effective debugging and searching feature, easy to detect the errors, also easy to configure. Here you can see a table view for easy debugging. Table view divided in two parts, transaction and transaction details. In transaction, there are multiple columns that will display all the transaction happened in the interface. On the top, we have a search option in order to search any particular address or CCC or any other column value in the entire simulation. Transaction details will provide much more details for a selected transaction. From the GUI display, we can see the master issues HDR command word at 24675 nanosecond, giving info, address, and read transfer. Then master send data words at 25435 nanosecond and 26235 nanosecond. Here you can see the another table view of HDR TSP. Multiple column display all the transaction happened in the interface. You can also see the decoded data is calculated for HDR TSP. So TrueY will help you to save from the unnecessary calculation, and also it will be less time consuming. In the bottom corner, we have an error count that will display the total error count in the entire simulation, and using these arrows, you can directly jump on the errors. This table view is one of the features in easy debugging. There are a lot of the more features for TrueY. You can contact for a live demo. Moving forward, these are the TrueChip I3C VIP deliverables. All the VIP components, master, slave, monitor, scoreboard are provided along with different type of test suites like directed, random, error injection, and dynamic test suites. In documentation, we provide integration guide for easy integration along with user manual and release notes. This is all about I3C. Thank you all for joining.